So now let's do 2.2. We said that the water has life-sustaining properties. And what was the first one that we mentioned earlier? When you compare water, H2O, to ammonia, NH3, with their mass, they are really similar actually. The mass of oxygen and the mass of nitrogen are very similar. With 3 hydrogens, they look like they are the same atomic mass. They weigh the same. But one evaporate at 25 degrees Celsius, like the ammonia on a perfume. They just vanish. But the water, it will not evaporate at 25 degrees Celsius. It will evaporate at 100 degrees Celsius. So that shows you there's something about the intermolecular forces of water. And we said last week we have intramolecular forces and these dotted lines between each water molecule and the next. You remember that? So that's what's going to make the water hold really tightly. So water molecules are polar and they have a slightly, so polar because we polarize to one side over the other on the covalent bond. Obviously, the oxygen is the bigger one, so it's going to polarize all the electrons to its side, and the other side is going to be more electropositive. So the charge distribution is due to oxygen tendency to attract the shared electron to itself. And water molecules form hydrogen bonds with other water molecules due to the opposite charges. Okay, water is hydrophilic. Water is hydrophilic. That means water is, that we say hydrophilic based on the concept that it dissolves in water. So water dissolves in itself. So polar molecules that interact well with polar molecules. We know that like dissolves like. So lipid are going to dissolve in detergent. Oil are going to dissolve in lipids. Water is going to dissolve salt because they all are polarized. Because you know in salt, sodium is plus, chloride is a minus. Does that look like a polarization? So that's the polarization. So they dissolve. Hydrophobic, meaning that the uncharged, non-polar molecules do not interact well with the polar ones. So oil is not going to dissolve in water. And there are non-polar substances. These are water-fearing. They do not dissolve in water, known as hydrophobic. So if you remember, so this same figure was on the exam. It shows you that water can exist as a solid, liquid, or a gas. So what's the difference then? In solid, the bond, you see, remember I told you, there is an intermolecular bond and there is an intramolecular bond. So we know that water molecules look like that. O with 2 H's. O with 2 H's. O with 2 H's. And we said that this bond within the water molecule is known as what? Is known as? Intra. Intra, because it's inside. Excellent. Intra. Is it covalent or polar? Polar. Polar covalent. It's covalent polar. I meant polar or ionic. So then it doesn't end that way because we know oxygen is electro what? Oxygen is electro what? Has a slightly what charge? Negative. And hydrogen is electro positive. Hydrogen is electro positive. Oxygen is electro. Hydrogen is electro. Hydrogen is electro. Oxygen is electro. Hydrogen is electro. Hydrogen is electro. But is this the only bond that exists in the water solution? Is this the only bond? No, because you know that's the negative and that's a positive. They're going to have a dotted relationship. That's a positive, that's a negative, they're going to have a dotted bond. That's a positive, that's a negative, they're going to have a dotted bond. That's why they have a lot of adhesion. These water molecules, they stick to each other, not just with the dash line, with this straight line, but also with the dotted line. We said the dotted line is what kind of of bond? Is it inter or intra? There's an inter between 1 and 2. Excellent. And this intermolecular bond, is it, what kind of bond is it? Is it covalent? Is it covalent, this bond, this dotted bond between the minus and the plus? What kind of bond is that? Is it covalent? I'm sorry? So did one give the other anything? We said ionic is one has to give the other a bond, an electron. One has to give the other an electron. Is one giving the other electron here? No. So these are known as dipole moments, dipole interactions, van der Waal interactions. These are interactions that are not covalent. They're not ionic, not covalent. They're not sharing, not ionic, because no one is giving the other. But this is an example of a bond that is a dipole. So there's a slight attraction, but not an actual bond. Just a slight attraction, like a magnetism. We call it dipole. That's a dipole. That's a dipole. Van der Waal. It's on the lecture slide, and yeah, it's on the book too. Van der Waals interactions. Based on, these are called dipole moments.
It's the same word. Dipole and van der is the same word.
So van der Waal is the name of the bond that is discovered by this guy, van der Waals. Yeah. But what is it scientifically? It's a bond between dipole moments. So there's a slight dipole. This is, because remember, we don't say bipolar. Bipolar is like when you have depression and you have, there's one depression and then you have anxiety. That's just bipolar. You have two poles. Here we say dipole, di. So it has dipole because one is minus, one is plus. It has two poles, like the North Pole and the South Pole. Dipole. Okay? So here you see the dotted lines. In ice, the molecules are the bonds are so close to each other. In liquid, they are farther apart. In gas, they are the farthest from each other. So that shows you the state of the matter in water. Water molecules form a crystalline structure. The structure is maintained by fixed hydrogen bonds. It makes ice less dense than liquid water. So it's very interesting because water is the same molecule, but when you change the phase, the density changes. When you put ice in water, why does the ice float? Because when you are solid, your density gets smaller. That's why the iceberg, 10% of the iceberg is 10% of the iceberg, 10% of the iceberg is floating and 90% is submerged below water. Same thing in a cup. In a water cup, you put an ice cube, you will see that this ice cube is actually 10% on the top of the water surface and 90% below the water surface. So that's why they say the tip of the iceberg, meaning the 90% is below, 10% is on top. Why? Because water density is 1 milligram per milliliter. But when it becomes ice, it drops to 0.9 milligrams per milliliter. So it loses 0.1. That's why the head of it is at the top. Ice floats on liquid water, creating an insulating barrier that protects aquatic life from freezing. Water is a liquid, so water molecules are packed tightly together. That's very important. We talked about that. We said that water molecules are so packed to each other, close to one another. Remember, that's water molecule 1. That's water molecule number 1. That's water molecule number 2. That's water molecule number 3. Number 1, number 2, and number 3. So even though they exist, you know, you can have a family, but the family doesn't only have family relationship. they have family with the next door neighbor. They have like a whole family, so they're all families that know each other. That's why in the wedding you see many families. That's what's happening in water. They all come together. So you have the one family, but the one family is dealing with having some dotted line. Is the family relationship with another family the same as interfamilial relationship between a mom and a dad and a son? No, it's not. Same thing with water. You have the covalent bond intra, but you also have intermolecular forces. If the intermolecular are so close, that means it's so sticking together like ice. If they are so far away, that means they are so liquidy like fluid like water. Now look at gas. Gas almost really no intermolecular forces with the adjacent water molecules. So the water molecules are on their own. It's like those families that barely talk to each other. They barely communicate. They talk like once in a while on the Thanksgiving, on the spring break. So that shows you, the gas molecules, they talk to each other every once in a while. But gas, but solid, they are so attached to one another. Then water molecules escape as gas. So when water boils, the water moves. So when you heat things up, the bond is gonna get weaker. So you go from solid bond to weaker bond, liquid bond, then you go to really, really, really a far separated bond. That's the gas bond. Remember, liquid and gas are both known as fluid. So fluid can mean liquid and gas. But liquid means you have to be closer to water. Liquid is like water. Gas is like air. But both of them are what? Both of them are? This point is important. So I'm going to ask you a true or false question. Liquids and gases are both fluids. Or solid, liquid, and gases are all fluid. You say that's wrong. Next slide. Specific heat capacity. We talked about that. We said that the amount of heat 1 gram of substance must absorb or lose to change its temperature by 1 degree Celsius. You need to know that definition for specific heat capacity. What does specific heat capacity mean? Specific heat capacity means that there is an amount of heat that 1 gram of substance must absorb or lose to change its temperature by 1 degree Celsius. So now water takes, so the definition is there, right? So in order for water to, its temperature to go up by 1 degree from 25 degrees Celsius to 26 degrees Celsius, it must absorb a specific amount of heat. It must absorb a specific 1 gram of substance that must be absorbed in order to elevate the temperature to 1 degree Celsius. So water has very high specific heat capacity. It needs 100 degrees Celsius to evaporate, while ammonia only needs 25. So water has a high specific heat capacity. It requires a lot of a lot of energy to increase its temperature, and it is caused by hydrogen bonding among the water molecule. So this hydrogen bonding, this dipole, you see this dipole van der Waals interaction, that is known as the hydrogen bonding. What's the name of this bond between the H and the O? Hydrogen bonding. Hydrogen bonding, because it involves a hydrogen. Specific heat capacity, we said, is the amount of heat is the amount of heat 1 gram of substance must absorb or lose to change its temperature by 1 degree Celsius. Water has a high specific heat capacity. We went over that. Now, there are warm-blooded animals. So water helps warm-blooded animals maintain a more even body temperature because water acts as a heat sink, absorbing and storing a large amount of energy from the heat. That's why we use it for sweating. Water can absorb a lot of heat without breaking apart and evaporating. So it's like a shield. It's like the actual sunscreen is your sweat because it absorbs a lot of heat. It requires a lot of heat for it to evaporate. So we need something like that, something very strong. So the heat of evaporation is a high amount of energy required for liquid water to turn into water vapor. So the heat of vaporization is the heat required to induce evaporation. So who's going to evaporate? Is ice going to evaporate? Water. So that means the heat of evaporation is always from the liquid phase into the gas phase. From the liquid phase into the gas phase. Water has a high heat. So I think it's best if you look at that screen so you know what I'm pointing with. So at home, when you go over the slides, it makes more sense. Water has a high heat of vaporization. It requires a large amount of energy to change from liquid to gas. So we said that the heat of evaporation is the energy required to break the hydrogen bonds holding the water molecules together. So do I break more hydrogen? So when I go from solid water, ice, to liquid water, do I break hydrogen bonds or no? When I go from solid water to liquid water, do I break hydrogen bonds or no?
Yes.
I break hydrogen bonds. When I go from liquid water to gas, what do? I break what kind of bonds? Hydrogen, more hydrogen. So you see, you break more hydrogen. So if you break hydrogen bonds in gas, you make liquid water. You break more in liquid, you make gas. What about if you go the other way? If you want to go from vapor to liquid, from liquid to solid, what do you do now? You make hydrogen bonds. Excellent. Excellent. That's we're going to talk about endothermic and exothermic reactions. So this energy is required to break the hydrogen bond holding the water molecules together. The benefits of high heat of evaporation. So the high heat of evaporation helps cool the environment through evaporation. So that's how you get cool when you secrete the sweat. So the sweat is now going to evaporate. So the sweat is going to evaporate and as a result dissipate the heat. So it's going to absorb the heat from your core and it's going to absorb the heat coming from the sun in order to evaporate on your behalf. So evaporating sweat carries away heat energy from the body, helping organisms cool down. Okay, it helps the organisms to cool down. So far, what are the properties, life-sustaining special properties of water? Number one, what was it? It has high specific heat capacity, which means that it is going to require a lot of thermal energy for it to For it, for the water to evaporate. Very good. It doesn't evaporate easily. Excellent. And the other way around, if you want to freeze it up, it's going to require a lot of energy for it to be frozen. Very good. So water is a polar solvent capable of dissolving polar molecules and ionic compounds. You see here, that's the O. You see where my mouse is? The O, they don't put next to it is, what's the electronegativity of the O? It is slightly what? Look here on the board. No, the O. Slightly negative. And the hydrogen is slightly. So when we want to dissolve sodium chloride, what is charge of the sodium? Is that a cation or an anion? That's a cation. This cation is going to bind with the hydrogen who's plus or the oxygen who's minus. Yeah, so now you see the oxygen is touching the sodium. The minus oxygen touching the sodium plus. You see here? What charge is the oxygen? Minus. Electronegative minus. Electropositive hydrogen. So if you look at my mouse there, you see that the oxygen minus touching the sodium plus. Oxygen minus touching sodium plus. Oxygen minus touching sodium plus. Here, chloride minus touching hydrogen plus. You see? So when it came to dissolving the sodium plus, the oxygen took care of that. When it comes to dissolving the chloride minus, the hydrogen plus took care of that. You see how water works to dissolve the objects? So charged particles form hydration cells, hydration shells surrounded by water molecules through hydrogen bonding. So ionic compounds dissociate in water, forming ions surrounded by water molecules. There is cohesion. Cohesion represents intermolecular forces between water molecules used by polar nature of the water. Cohesion is intermolecular forces between water molecules caused by the polar nature of water. So you see this cohesion we talked about, and we use cohesion for water being high specific heat capacity because it has high cohesion. They are so close to each other. That's why they don't dissolve. They don't break apart easily. And cohesion allows the surface tension, enabling water to resist rupturing when under stress. That's what we use in the heart. So the heart has a capsule around it full of water. It has a sac. It has known as pericardial sac. This pericardial sac around your heart is full of watery, called serous fluid. Serous means it has water, electrolytes, proteins, and so on. Are we clear? The lung also has a capsule around it full of serous fluid. Clear? So why? Because water has adhesion. It will adhere to the lung and to the heart, preventing any rupture. So your heart is beating against the rib cage. So if it didn't have this water cushion bag around it, it will rupture. The lung also inflate, deflate. It has this protective cushion bag full of water around the lung. Surface tension allows some objects to float on water despite being denser. So this insect here is supposed to drop and sink to the bottom, but it can float. Why? Because of this surface tension, because the water molecules have hydrogen bonding so tight to one another, they can float on top of them. But if you have alcohol and this insect think this is water, it will touch it, it will sink. Because alcohol molecules don't have these intermolecular hydrogen bonds. that have high surface tension. So surface tension means the water molecules are so touching one another that it makes tension force on the top that allows for objects to float on top of them even if they are denser. That's how you have the boat. The boat is more dense than water, yet it floats on water.
One of the six.
I'm sorry?
Which one of the six?
Which one of the what?
No, I'm asking, you said it's allowed to resist, but I'm asking you which one of the six?
That's the surface tension.
Surface.
The surface tension allows some object to float and stick on the top of water, even though they're heavier and denser. Yeah. Adhesion. So there's an attraction between water molecules and other molecules. So that's what we talked about. Adhesion is like around your heart and around your lung. It's like a water cushion, water bag between the water molecules and other molecules. Often stronger than the surface tension. It causes water to climb up narrow tubes. So if you put a paper slip on a water cup, the water is going to start seeping, moving up. With peristalsis, it's going to start seeping and moving up through this paper. So because water is sticky, it's going to stick to each surface and it's going to climb it. So that's an example of adhesion. That's the adhesive property. So on the exam, which property allows the water to climb up the narrow tubes or climb up a paper? That's adhesion, because it's going to adhere to that surface. Whether it's a glass tube, whether it's a paper, it's going to adhere to that surface. Water adheres to charged surfaces, such as the inside of a capillary tube. So why does water adhere? Because this glass has a charge. The paper has a charge. So the charge, remember, water dissolves like. Water is polar, it dissolves polar substance. So if you have a thin film made of oil, water is not going to climb it. But if you have paper or you have glass, glass is charged, is polar. So water is going to climb it. Yes.
The example I read somewhere in the slide with the paper towel being able to soak in the water.
Yeah.
Is that cohesion?
The paper, we just said, if you have a oil film, you put it, the water is not gonna climb it. But the paper towel, it was able to adhere, stick to it, from the word adhesion. So it was able to stick to the paper towel and move through it. That's what soaked it. You understand? Due to the adhesion. Because we adhere, we stick. We stick. Okay? And that's how soap works. What happens is dirt, polar or non-polar. Dirt is non-polar. Dirt is oils and non-polar and crap. So when you put soap all over you, soap has a core that is non-polar. So all the soap is going to start adhering to the non-polar oil and nasty stuff and all the bad crap. Then when you pour water, so soap is a hybrid, 2-in-1. Soap has a non-polar part. Soap has a non-polar part, and it has a polar part. And here you have dirt. So you put soap all over your body, and the dirt is non-polar. So the non-polar part of the soap is going to stick to the non-polar dirt. Is that part clear? Then when you pour water, water is polar. So water is going to shove and push down the polar substance, moving everything down, flushing everything down. Make sense? So we used water to dissolve the polar part of the soap. And we use the non-polar part to dissolve the dirt. So it's like a hybrid, 2-in-1. Soap is 2-in-1. Some part is non-polar, some part is polar. So we use the adhesion property of water to adhere to this polar part, push it down. And we use the non-polar property to dissolve all the dirt and all the the oily substance. Okay, the pH. pH measures the concentration of hydrogen ions. So pH is negative the logarithm of the hydrogen proton concentration. So what does that mean? That means a change by 1 degree in pH, meaning 10 orders of magnitude, million times increase in the hydrogen proton concentration. So you need to know that the pH equals negative the log of the hydrogen proton concentration. Pure water has a neutral pH of 7. That one is golden. Water is right in the middle. Our pH goes from 1 to 14. Who's number 1? That's also a very high yield. You will see this forever. The stomach acid that break down the food, that chemically digest the food in your stomach, has an acidity of 1. So acidic. While water is right in the middle. It has 7. So water is not acidic. Water is not basic or alkaline. It is neutral. Water is right in the middle, 7. And that shows you a spectrum. So the battery has pH 0. The stomach acid has pH 1. Lemon has pH 2. 3 is the vinegar. Coffee is 4. The blood has a pH 8, so the blood is slightly basic. So this spectrum, so if I bring this paper, if I bring this figure on the exam and tell you, is acid more acidic than vinegar, or is vinegar more acidic than acid? So there's 2 poles, that's bipolar. Acid, the farther you go to the left, the farther you go down. This is really important. The lower the pH, the more acidic you are. The higher the pH, the less acidic, the more basic you are. The more alkaline you are. Basic is the same thing as alkaline. The same tomato. The same way we said atomic number and proton number is the same thing. Basic and alkaline is the same thing. So the question is 5 more acidic than 4, or is 4 more acidic than 5? Very good. Is 5 more basic than 4, or is 4 more basic than 5? Yeah, very good. So now you got it. What is the pH of water? What's another pH that we really need to know? The blood. Our pH is around, it's actually not 8. It's 7.35 to 7.45. So it's slightly acidic or basic or neutral. The pH of the blood is 7.35 up to 7.45. If your pH of the blood goes below 7.35, like 7.25, you have a disease called acidosis. Acidosis. And acid in the blood, acidemia. If you hear what's the difference between acidosis, is a metabolic defect. Acidemia means just the blood. So hypoxemia means drop in oxygen in the blood. Hypoxia is dropping oxygen in the tissue. Acidosis, drop in hydrogen, drop in pH, and an increase in hydrogen proton. So another question is, who has more hydrogen proton concentration? 1 or 2? 1. Who has more acidity? 1 or 2? Who has a lower pH? 1 or 2? No problem. So the acid has a pH lower than 7. Hydrogen proton is more than the OH, and the base has a pH that is more than 7. Okay. Acids are substances that donate hydrogen protons to a solution. So an acid, it has so much hydrogen proton, it can donate. A base can accept hydrogen proton. A base can accept hydrogen proton. Or it can donate OH, hydroxyl ion. So a base has two definitions. It will accept hydrogen proton, and it will accept hydrogen proton, and it will donate. What will it donate? Hydroxyl, OH minus. It has two definitions. So if I say a base has high hydroxyl concentration, that's true. It has a low hydrogen proton concentration, that's true. Because otherwise, how is it going to accept hydrogen proton if it has already too much? It must have low hydrogen proton concentration. So now strong acids, they are rich in hydrogen proton. They donate a lot of hydrogen proton. While weak acids, they are poor. They donate just a little bit. The bases, there's weak base, weak acid. A weak base donate just a little bit of hydroxyl, OH, or accepts just a little bit of hydrogen proton. But the strong base will accept a lot of hydrogen proton or donate a lot of OH. Very good, OH.
Base, donates again, you said.
OH, hydroxyl, OH, Hydroxyl, hydroxyl. These are substances that accept hydrogen proton or donate hydroxide ions. You see right here, look. Bases, substances that accept hydrogen proton or donate hydroxide ions, OH minus, to a solution. So strong bases donate readily a lot of OH minus, such as sodium hydroxide. So that's the biggest base. You need to remember that. The strongest acid is who? If you look at this, who's the strongest acid? Acid. No. The acid is zero. The strongest acid in your stomach, that's HCl, hydrochloric acid. The strongest acid has a pH of 1. That's the stomach acid known as hydrochloride. H, capital H with Cl, hydrochloric acid. Acid is hydro HCl, HCl, hydrochloric acid. Hydrochloric acid. That's the strongest acid. It has pH 1. The strongest ever base, the strongest base is NaOH, sodium hydroxide. It has a pH of 15. That's the end of the, these are the two enemies, the two end of the spectrum. Yep, sodium with hydroxide ion, OH. Now you need to know that acids are substances that donate hydrogen proton to a solution. They have one definition, acids. They donate hydrogen proton to a solution, hydrogen ion to a solution. Strong acids donate a lot. They are rich. So strong acids are rich in hydrogen proton. Such as, who do we say? Please look at my mouse. Hydrochloric acid. That's a very strong acid. Where we find hydrochloric acid? In the stomach. Weak acid, like in the tomato juice or the vinegar, they do not completely dissociate. Now, bases. Bases are substances that accept hydrogen proton or donate hydroxide ions to a solution. Or donate hydroxide ions to a solution. Strong bases readily donate OH minus, such as sodium hydroxide and household cleaners. Weak bases like seawater have a pH close to neutral. Now buffers, they resist change. So if you put hydrogen proton in a buffer, it's not going to change. It's going to resist the change. So they absorb. They are bipolar absorbers. They are bipolar absorbers. They absorb acid, hydrogen proton, and they absorb hydroxide ions, OH. So they always maintain neutral pH. Neutral pH. They are so I need you to look at the screen because that's you're looking, that's good, that's very good. So you have an iPad. Yeah, good, very good. Yeah, I saw that, very nice. Hydrogen proton, so they are buffers, so they resist change. That's the one thing you need to know. So if you add acid to them, they will absorb the hydrogen proton, they will never change. The pH is not going to go down, so they remain neutral at 7. So the buffers are always near neutral at 7. You add acid, they stay 7. You add base, the pH supposed to go up. You know, when you add acid, the pH supposed to go what? Up or down? With acid. But supposed to go down. If you add acid, the pH goes down. Except it's a buffer, you add acid, it's very stubborn. It's not good, it's gonna stay 7. If you add base, it's supposed to go up. But the buffer is stubborn. It's going to stay at 7. And we love that because our pH is supposed to be, our blood pH is supposed to be what? Neutral. So we have a lot of buffer in our body. So when by mistake there's too much acid, that means it's going to stay at 7. Unless you take too much acid by like a suicidal, taking then that's dangerous then. That's overwhelming the buffer capacity of your blood. So antacids act as buffers, even though they call them antacids, but they're actually antacid, antibase. Buffers are bipolar resistors. They resist acid, they resist base, they're stubborn, they stay at 7. They absorb excess stomach acid too. So when you have heartburn, you have too much acid burning your esophagus, burning your stomach. So you take an antacid to cool it down. Otherwise, it's gonna corrosive. It's gonna injure your esophagus. So the buffer system in the blood prevents it from becoming too acidic and too basic. Excessive hydrogen proton in the blood combined with bicarbonate ions. So excessive hydrogen ion right here. This is really important. It's telling you that excessive hydrogen, you see where my mouse is? Excessive hydrogen proton in the blood combine with bicarbonate. Where is bicarbonate? This is bicarbonate. So excessive hydrogen proton, if you're preoccupied with writing and you don't understand, this is recorded. You can go home, write at home at your own pace. Now listen and look there to understand. You shouldn't be writing anything. You can go home at your own pace, write. Because I'm explaining a very important concept. You will see it on the exam, but you're writing. So look there, stimulate your mind, learn, go home, sit down, write as you want. So now excessive acid, you see where my mouse is? Excessive acid, excessive hydrogen proton in the blood combined with bicarbonate ion. Where is bicarbonate ion? Right here. HCO3 minus. You need to know that bicarbonate ion is HCO3 minus. And this is the excessive hydrogen proton. So the hydrogen proton is going to stick to the bicarbonate. Now the bicarbonate now is going to become acid because it accepted hydrogen proton. So now it's gonna convert. You see, it used to be H. If you see where my mouse is, it used to be HCO3. It accepted an extra hydrogen proton. Now is H2CO3. Some students, they look at H2 here. They say, oh, there's 2 hydrogens. there is a bi. This is bicarbonate. No. The one with the one hydrogen is the bicarbonate. The other one with the two hydrogens is the carbonic acid because it accepted the hydrogen. It's acid now. It can now donate it too. This hydrogen product, it can donate it. Then your body is going to recycle. So let's recycle H2CO3. Let's recycle. How do we recycle H2CO3? H2CO3. What is that? What is that? Is this bicarbonate? This is carbonic acid. Carbonic acid. How do we recycle that? We have two H's and we have how many carbons? In carbonic acid, how many H's do we have? Two. How many carbons do we have? Who said three? How many carbons do we have? How many oxygen do we have? Three. Oxygen, oxygen, oxygen. So how can I recycle that? What do we love? We love water. Water is H, and O. So let me take out H2O. What is remaining? CO2. That's carbon dioxide coming out my body, and I keep the water. So you see how your body can repair too much hydrogen? So you have too much hydrogen, is going to bind with bicarbonate, which is H. What is bicarbonate? What is bicarbonate? HCO. HCO3. You see there? HCO3. Did I tell you it's the end of the world? Okay. Okay. So look, this is the very important buffer. So what's going to happen is it's going to take this excessive hydrogen, and now we're going to have H2CO3. What do we call that? That's our carbonic acid. Then we recycle it into the water. We love the water. The water is neutral, making my blood neutral. And what am I going to do to the carbon dioxide? I'm going to expire it. Come out. So now you see how buffers work in our body. This is very good, very important concept to know. Water's unique properties, including polarity, hydrogen bonding, and high heat capacity. So you need to know these properties. Polarity, so that it can dissolve. If it's not polar, if water didn't have minus oxygen plus hydrogen, it can dissolve anybody. So it needs to be polar. One oxygen needs to be really minus, one hydrogen needs to be really plus, so that when you put NaCl, the minus oxygen can bind with who? The minus oxygen can bind with the Na or the Cl? With Na, very good. And the hydrogen electropositive is going to bind with the... Okay, so in water, who's electronegative? Oxygen or hydrogen? Who's electropositive? And being electronegative, electropositive, having a relationship with another water family. So it's not in, it's intra. That kind of bond is, what kind of bond is that? What's the name of that bond? The dotted line bond. It's the dipole, van der Waals, but it's, what's the name, the main name? That's it's van der Waals. If we say van der Waals, if we have the same concept with other atoms. But if you have it with hydrogen, we change from van der Waals into hydrogen bond. It's called hydrogen bonding. So hydrogen bonding is like a dipole interaction, hydrogen bonding. It's like a dipole interaction, but since it involves just the hydrogen, we call it hydrogen bonding. But if it's some other compound, sodium, with somebody else, we don't call it hydrogen, we call it van der Waals. But the same concept. No, if you have this kind of interaction between somebody electronegative, somebody electropositive, but it's not a covalent bond, that's an example of a dipole, because one is a minus pole, one is a plus pole. If one of the dipoles is hydrogen, we name that hydrogen bonding.
Okay, only if one of the dipoles is like.
Exactly. If one of the participants in the dipole moment is hydrogen, that's hydrogen bonding. If it's not hydrogen, between any other two random molecules, we call that van der Waals. Van der Waal. And we use van der Waals for like proteins, flipping them and rolling them and converting them from primary to secondary to tertiary structures. Okay, water rolls and dissolving substances, they have cohesion. So cohesion is what enables the insect. But when the water climbs up the paper and climb up the glass, what kind of adhesion? Adhesion based on what? Why didn't the water adhere to an oil film? Why did it just adhere to glass and paper? Excellent, because it had a charge. Very good, very good. Okay, so that was the first one. Now the second one. So we're done now with 2.2. Yeah. Two 2.3. Now we're going to talk about the importance of carbon. So cells are composed of macromolecules. These macromolecules are known as proteins, nucleic acids, carbohydrates, and lipids. So you're either a fat, you're either a sugar, you're either a nucleic acid, or you're either a protein. If you are a macromolecule, you're either one of those four. So you got to know these four families: nucleic acid, carbohydrates, lipids, and proteins. And if carbon is found, if carbon is found in any molecule, we call that organic. That's an organic molecule. That's an organic molecule. It's a carbon-based molecule that is essential for life. Carbon-based molecules are essential for life. Carbon's ability to form up to 4 covalent bonds makes it the ideal backbone for these crucial macromolecules. So carbon can please remember that carbon has the capacity to form up to how many covalent bonds? 4. It makes it the ideal backbone for these crucial macromolecules. Carbon's incomplete outer shell allows the formation of up to 4 covalent bonds by sharing the electrons. You see, these are 4 covalent bonds that share the electron. So you see, carbon is not like oxygen. It can have those 3 bonds. You see, carbon is blue, it's giving in a blue electron. Hydrogen is red, it's giving in a red electron. So that's 1 bond. North, that's the second bond. South, east, west. You got it? Do you got it? Do you get it? Very important. You know, if you're looking into your iPad and you're not looking where my mouse is, you're still missing out. So it's best if you can look at your iPad and look at my screen, then you get the maximum. And like I said, don't be preoccupied with writing. This is going to be posted. This is not classified White House secret information that will be seen. I'm going to post it. You're going to see it. So you don't have to write anything. Just stimulate your mind. Look and understand, absorb the information visually, then go home and write. Because I'm afraid while you're writing, you're missing out on something.
Like, can you at least say the key points so we can write that at least?
It's on the video.
No, what you like, study that, so we can write that.
Yeah, I'm gonna mention it as I'm
I
speaking.
watched the video.
Yeah. Okay, hydrocarbons, from the name, that's a hybrid. There is a hydrogen and a carbon. A hydrogen and a carbon. Consists mainly, entirely from carbon and hydrogen. These are hydrocarbons. We burn hydrocarbons like the gas, fuels. So stored energy in covalent bonds are released during combustion. Stored energy in covalent bonds are released during combustion. So methane's tetrahedral shape allows carbon chain backbones to form, creating the framework for biomolecules. So backbones can be linear, cyclic, or combinations of both. So they contain single, double, or triple bonds, affecting molecular shape and function. So that shows you hydrocarbons. It's made up of carbons and a hydrogen. So there are chains of hydrocarbons. So they are linear or branched. So they can be linear like that or branched like that. So single bonds allow the rotation. Double and triple bonds do not and result in planar and linear molecules. So prefixes denote carbon number with F means 2 carbons. F means 2 carbon. Suffixes indicate the bond type. Ane is for a double bond. Ene is for ane is for a single bond. Ene is for a double bond. Ein is for a triple bond. We will talk about that. So the beginning means how many carbons are there. So ethane, it means there is 2 carbons, and the bond between them is a 1 bond. Ethene is still 2 carbons, and the bond between them is a double bond. Ethine is still 2 carbons, and the bond between them is a triple bond. And these are the shapes of the methane tetrahedral. Ethane is also tetrahedral. Ethene is planar. While ethyne, the bond, so if you have a double bond, does that make you stronger than a single bond or weaker? Stronger. So the more bonds, the more stable you are. The less bonds, the least stable you are. There are aliphatic hydrocarbons. These are linear chains or rings with a single, double, or triple bonds. So they have, so these aliphatic, they are cyclic. So you don't have a linear chain like that. You don't have a linear chain like here in aliphatic hydrocarbons. These hydrocarbons are now cyclic like a cycle, but there is no double bond. So the linear chains or rings with single, double, or triple bonds. You will see that always in the aliphatic hydrocarbons, there is single, triple, or double bonds. But in the aromatic, that's what we use in a perfume. Aromatic hydrocarbons are used on the perfumes, and they are cyclic carbon chains with alternating. So these bonds don't stay in one place. They keep shifting from one place to the other. Keep shifting from one place to the other with alternating single and double bonds because the electrons are delocalized. So you look at benzene. Benzene rings are in many biomolecules, amino acids, cholesterol, and some hormones. And they're also found in the herbicides and the crude oil. We find them in the perfume, the herbicides, and the crude oil. What are isomers? Isomers are molecules with the same chemical formula but different atomic arrangement. You have the same chemical formula but different atomic arrangements. Structural isomers. Structural isomers have the same chemical formula but different bond replacement. So do you understand the difference between the isomers? These are molecules with the same chemical formula but different atomic arrangement. But structural isomers, they have different bond placement. So the bonds are different in structural isomers. So butane and isobutane both have the same chemical structure, but they have unique properties. Butane is a fuel, and isobutane is a refrigerant. So if we look now at the geometric isomers have identical bonding, but different bond placement. Like here you see both of the methyl groups on the same side. But here you see one methyl on the bottom and one methyl on the top. Methyl groups on the same side, methyl groups on opposite sides. So cis-2-butane, so that shows you these are geometric isomers. Common isomers, these are the triglycerides. So triglycerides are fatty acids that may have cis or trans double bond. They have cis or trans double bonds. So the cis represents unsaturated fats. The bent shape prevents packing, and oils stay liquid at room temperature. Oils stay liquid at room temperature. Trans fats, they are unsaturated. So here the cis fats, meaning the carbons are on the same side, like here. That's cis. If both are on the same side, that's cis. But if both are on the opposite side, that's trans. So the unsaturated fats, they are cis. So both their bent shape prevents them from packing, prevents the packing, and the oils stay liquid at room temperature. But the trans fats, their linear bond allows them to pack, and the oils are solid at room temperature. These are linked to the heart disease. So that's the question to ask on the exam. Which of the two fats, cis fat or trans fat, is bad and can cause heart disease? And the answer is trans fat. There are saturated fats. That's another important question. Saturated fats are saturated with what? Saturated with hydrogen. So saturated fats, they have no double bonds, and each carbon is saturated with hydrogen. It is solid at room temperature and typically animal-based. The saturated that's a saturated fatty acid. That's an unsaturated fatty acid. And this is a transoleic acid. What are enantiomers? Enantiomers. What are enantiomers? Enantiomers are molecules that are mirror images of each other. So they have identical chemical structures and bonds, and they differ in three-dimensional orientation of atoms around the central carbon atom. And they appear flipped. So they are not superimposable. They are not superimposable, these enantiomers. So you cannot put two enantiomers on the top of one another. because they are mirror images. So for example, if you stand in front of the mirror and you take a photo of yourself, that photo, can you stick it to your face? Because no, it's gonna be a mirror image, cannot be superimposed. So those two, the D amino acid and the L amino acid, these are two mirror images, so they cannot be printed on one another. So now we're going to talk about chirality. What is chirality? Chirality means north, south, east, west. They're all different. Meaning, look at my carbon. My carbon is in the north, bind to fluorine. West binds to hydrogen. South binds to chloride. East binds to bromine. So now these are all different. If you had two hydrogens, so that means two of the bonds bind hydrogen, that's achiral. Chiral means all the bonds are different. You're dealing with four different bonds, like here. That's the perfect example of a chiral molecule. Carbon fluorine, carbon hydrogen, carbon chloride, carbon bromine. Is there any duplication here? They're different. But if you remove bromine, put fluoride. Now you have two fluoride. Is that chiral? What is that now? Achiral, achiral, achiral. You got to put an A before the chiral. So the D forms of amino acids are present in bacterial cell walls. D form of the glucose is the photosynthesis product. We rarely see the L form in nature. Functional groups. Functional groups. Functional groups are groups of atoms on molecules that confer specific chemical properties to those molecules. So functional groups are groups of atoms on molecules that confer specific chemical property. So now look at the OH. That's a functional group known as what? You got to know all these functional groups. You're going to see them again. Today, my test on anatomy and physiology 1, if you're going to take it next semester with me or with any other professor, they're going to show you this, ROH, and ask you, what is that? Is that hydroxyl, methyl, carbonyl? That's a hydroxyl. So this hydroxyl group is definitely going to make that molecule a polar molecule. Because you know the oxygen is polar. So that's the hydroxyl functional group. What about the methyl? The RCH3. That's an example of a nonpolar. Carbonyl. That's an example of a O. You see when there's O, that's like an example of a polar, of a polar molecule. But that's known as a carbonyl. Carboxyl. It has a carbonyl and a OH. Amino. It has a nitrogen with two H's. Phosphate. Definitely got to have what? A P. Phosphate. Sulfhydryl. That's the easiest one because it has sulfur. Phosphate because it has phosphate. So these structures, you got to sit down, right? You got to sit down and look at them. If I see a molecule and they ask me, what functional groups are there? If there is an OH, that's a hydroxyl group. If there is just a carbon, that's a methyl group. If there is an oxygen double bonded with a carbon, that's a carbonyl group. If there is a carbonyl and a hydroxyl in the same carbon, that's a carboxyl. If there is a nitrogen, that's an amino. If there is one phosphate, that's the easiest one. That's a phosphate group. If there is one sulfur, that's a sulfhydryl group. So that one, you got to sit down for that one. You're not just going to get it by looking at it once. You got to sit down and know these functional groups. They're going to go with you long way to farm, to anatomy and physiology. All the medications are working on these functional groups, which ones are polar, which ones are non-polar, which ones are going to dissolve, they're going to bind which receptor, polar, hydrophilic, hydrophobic. So attached to a macromolecule carbon backbone, and there are substituted hydrocarbons. So they are substituted. So you have the central carbon, attached to it, you have these functional groups. So proteins, lipids, and carbohydrates and nucleic acids each have a characteristic set of functional groups. That what makes them different. So the functional group, this is hydrophilic and hydrophobic, don't dissolve. You see, there's oil in water. Water is hydrophobic, hydrophilic, and oil is hydrophobic. They never mix. They never mix together. You see this in cultures too. Some cultures, they never mix, they never get along. That's true. But same cultures, they always mix together. They always get along. Friends who have the same mindset, they flock together. Birds of the same feather flock together. If they have different ideas, they don't flock together, they don't come together. So methyl groups make molecules hydrophobic because methyls are not polar. Remember them. So now you gotta know. So now they're gonna tell you in that language, methyl. If you don't review this, you will have no idea what methyl is. They're not gonna tell you that carbon with another CH2. They're just gonna tell you methyl. You gotta know what that is. So a methyl is gonna make you polar. Amino. You see now they told you amino. They never said a carbon with an N next to it. They just said amino. Carboxyl. So you know carboxyl is a carbonyl with an OH. You see? Carboxyl. Carbonyl with an OH. Carbonyl groups make molecules hydrophilic because they have an oxygen. So that's polar. That's going to dissolve in water. So now look, that's the kind of questions we ask. So you're going to see this structure, and you're going to see an arrow pointing here. What is that bond? What is this functional group here? That's a carbonyl. That's a carbonyl. What is this? That's a amino group. What is that? That's a hydroxyl group. What is that? That's a phosphate group because it has a P, and so on. So don't get intimidated by this whole big molecule. You should be able, by knowing these structures and their names, to tell which one is which. So the interactions between the functional groups help maintain the structure of the molecule. That's how we will see the protein folding takes place. So the carbon's ability to form 4 covalent bonds is central to its role in the biological molecules. You gotta know that. You gotta know that carbon has the ability to. I ran 10 miles last night. I don't know how to walk anymore.
How long did it take you to do it?
It took me about 3 hours.
What?
Yeah.
Now
The
you're
first hour I ran 6. Then after that I just did
You walk.
3. Yeah, I walked.
That has to be. You could do 10 miles in less than 2 hours. I know you can.
Yeah. Actually, no, I did it. I actually did. I actually did 11 in 2 hours, but now I'm too tired.
No, 2 hours. But you said 3 hours it took you for 10 yesterday?
Yeah, because I was working. I'm tired.
I get it.
But if I just wake up, I can do it in
And
2
you
hours.
get straight to it? Nah, you probably do it in an hour and a half.
Tonight I'm gonna try to do 4. You know you gotta exercise, guys.
I'm gonna run
Especially
10 miles next week and I'll tell you the time.
one time a week. You gotta do it one. You gotta do this every day.
Best time in 10 miles is like an hour and 20 minutes.
You did 10 miles an hour, 10 minutes.
Hour like 28 minutes, something like that.
28 minutes.
Yeah, an hour and like 20 to 20.
Wow. No, I cannot do that.
I think it's, oh, I got an old age.
Okay, guys. You know you gotta exercise. You know you gotta, if you don't exercise, you don't stimulate your bones are gonna be weak and you're gonna get osteoporosis. Guess what do you need? What do you need? I can't walk, remember? What is it? What's the question? Okay, it's about your grade?
No, it's
Oh.
about the thing.
So ask so everybody can learn. What thing?
No, I was.
Pull up that thing on there so she can tell you.
What is it?
All the different connected bonds.
These?
Yeah.
This one?
The OH what that would be on the functional.
This one, the OH?
Yeah.
You see,
The,
hold on. You see this table I said you gotta look at, sit down? The OH.
I'm sorry.
So look, OH is hydroxyl. But if you have OH with another carbonyl, that's no longer hydroxyl. That's a carboxyl because you're mixing both. You're mixing a carbonyl.
The one I'm missing would be carboxyl.
No, because that one just has an OH. In order to be carbonyl, you have to have, in order to be carboxyl, you gotta have a carbonyl, oxygen with double bond, like right here, and the OH. That makes you carboxyl.
Okay.
Okay, got it.
Okay, so that's what I said. You're not gonna get it from the first time. You gotta sit down and examine it really well. Okay. The carbon binds covalently with oxygen, hydrogen, and nitrogen to form crucial biomolecules. Carbon and hydrogen can form hydrocarbon chains or rings. So remember the aromatic structure. One of them has fixed single, double, triple bond. One of them has alternating. What's the name of the alternating one? We said already, the alternating double bond is known as hydrocarbon, aromatic. You see? Right here. Look at aliphatic. Aliphatic, they have linear chains or rings with single, double, or triple bond. Aromatic have cyclic hydrocarbon with alternating single, double bond. So the double bonds keep flipping from one place to another. That's aromatic. So that's the stuff that you got to focus on. And functional groups are atom groups that, when attached to the hydrocarbon backbones, they confer specific chemical properties. So these functional properties, these functional groups right here, you gotta know these functional groups because what's gonna make glucose polar, what's gonna make a triglyceride nonpolar, what's gonna make the DNA phosphodiester bond is these groups. So you gotta know a hydroxyl, you gotta know a carbonyl. So it's not something you will know now. It's something you sit down and inspect it and repeat it. That's how you're gonna get the information.